Okay, the recording has started. Gizem, thank you. The stage is yours.
Okay, thank you. Okay, so today let's just start with thinking over what we did. The very first lecture, we talked about the geometry, and we saw that the Suture geometry had two boundaries, one at late times, one at early times. And the second day, we talked about the symmetries, and we saw that the Suture symmetries fall under one of the class of Lorentz groups. It falls under the SO1, D plus 1 for isometries of D plus 1 dimensional de Suture. So today we talk about its representations, and our goal is to, so the beginning of the lecture, or most of the main material of the lecture, will be introducing to you the concept of representation and giving you general remarks about the representations of this group, SOD plus 1, 1. But hopefully there will be time enough such that I can show you at least one example of how to realize, how to see these representations in terms of, for instance, the fields we are more used to working with. So hopefully we will manage to get there. But so, as always, let's warm up with some basics. So what is a representation to begin with? Now, a representation of a group is a map from the elements of the group to some matrix group, actually. And this map has it's not just any random map, but it's a map that preserves structures. So what is this? Okay, so say this is our representation. So it has entries from the group elements, and then this GR stands for general linear transformations over some vector space V. This just means at the end of the day, your representations are matrices that have inverses. They're invertible matrices, and that's they themselves form a group. That's what this GLV is. This is a group of matrices. But let me warn you from the beginning, these matrices do not need to be finite dimensional. They can have infinite number of rows and columns, so to say. Now, what is this? What does it mean to have a structure preserving map? These maps are called homomorphisms. Morph is a Greek word for structure, and homo means similar. So like even the name, it says it even in its name. But what does this mean? If you take two group elements, and if you, so these are group elements, and if you look at the representations of these group elements and you perform this operation, now these representations act on the elements of the vector space, that is involved in the map. So if you look at the product of two representations, it gives you another representation such that the entries follow this structure. So it's the structure of the entries that is preserved. Now let's consider an explicit example, and this has sort of become the theme of this lecture series. We always do things in 2D because it's simpler. This might also be a good point to keep in mind even in active research. Well, let's just talk about rotations in 2 dimensions. Now we know if we rotate x and y coordinates by some angle theta around an axis perpendicular to them, this is how the new coordinates, x prime, y prime, look like in terms of the old coordinates and the angle of rotation. So this is our parameter. The parameter. So for each angle theta, for each value of theta, we have a different element from our rotation group. But these equations we can write in terms using matrices. So we can write it like, let's call R this vector xy. So we can say that R prime is just, no, everything is R. This capital R of theta acting on R vector, okay? Now, we've written down a matrix. So is this a representation? That's the first thing to ask. To check that, okay, it's a matrix. We were expecting a matrix, fine. But does this preserve structure? That means if I perform 2 rotations. Now, what do I know about performing 2 rotations? I rotated starting from here by an angle theta 1, my first rotation. And then I rotated once more, my second rotation, by another angle theta 2. So altogether, this is a rotation of theta 1 plus theta 2. So the parameters of the individual group elements get added up. So this is the structure to preserve, the adding up of the parameters in the case of rotations. Now, in fact, look at these. So if we perform 2 rotations, we just multiply these 2 matrices that we used as the representation of individual rotations. And you just do some trigonometry and you come up with the fact that the angles indeed just get added up, okay? So it does preserve the structure. Moreover, this is the structure we expect. So this is our homomorphism at hand. Now the representations of SO2 are, okay, I'm going to say things. So these are matrices, but they can be like, they could have been functions. Can you say like function valued matrices that satisfy this condition, this. Now note that exponential functions automatically work like this. If you multiply 2 exponentials, you end up with an exponential where the arguments of the individual exponentials are added. So this automatically satisfies our condition, the structure for the rotations. Now take this as a hint. Now we found this rep in terms of this 2 by 2 matrix. A concept is whether it's reducible. I mean, is this the most fundamental elementary way to represent a rotation, this 2 by 2 matrix? Now, technically, a representation is irreducible if it has no non-trivial invariant subspaces. That means, okay, an invariant subspace. So remember, these are defined over some vector space V. An invariant subspace is a portion of this vector space that keeps getting mapped to itself. So you do some transformations on it, but it doesn't change, hence the invariance. Now, so you look at your whole vector space and you ask what are its invariant subspaces. If this is just the null space and the full space, you know, always a space is its own subspace. The null space is a subspace of every space. And then, you know, there might be some other spaces. But if the invariant ones are just this, the null space and the full space itself, then it means it has no non-trivial invariant subspaces. So this is the technical definition. But more practically, it means that these representations that, you know, you can write down as matrices, if you can diagonalize it, that means you can break it down to smaller representations. That looks like you just took smaller matrices and stitched them together. So let's see, like this, M1. And these don't need to be all of same dimensions. This can be like 1 by 1, 2 by 2, I don't know, some other 1 by 1, so something like this, and all zeros everywhere else. Then this, if you can put a matrix in this form, this means this is this is composed of these smaller submatrices. This is called the tensor product. In fact, for those of you taking advanced quantum mechanics, oh, sorry, what happened? Okay. Zoom is getting tired. Okay, sorry about that. I think maybe I pressed something by mistake. Now, if you are taking a advanced quantum mechanics class, this is the picture you see in front of Sakurai, if that's your book. That's actually what it is referring to. And somewhere inside the book, it talks about this when it talks about spin. But so in practice, this is what it means. But if you're given a matrix, you're told this is the representation. If you can diagonalize it, it means it's a reducible representation. If you cannot diagonalize it, that means you have your irreducible representation at hand. Now, this rotation matrix we have at hand, to diagonalize it, that means finding its eigenvalues and eigenvectors, and using the eigenvectors, you can diagonalize the matrix. And in the end, it will have its eigenvalues at the diagonals. Now, you can calculate the eigenvalues for this rotation matrix we wrote down. And it turns out that its eigenvalues are e to the minus theta and e to the plus theta. So just exponentials. And you see, they just sit at the diagonal. So each one of this is an irreducible representation. And these are just, if you like, these are mini 1 by 1 matrices. So these are one-dimensional objects. But now notice that this e to the plus minus I theta is just one among many, many solutions that will satisfy our structure. So any e to the I k theta will work, will solve this. Moreover, we know that to rotate by 0 degrees and to rotate by 2 pi is the same thing. So this should also show up in our representation. So that means just setting e to the theta equals 0 equal to e to the I to k. And this is satisfied so long as k are integers, or real integers. So actually, we found that for the pure rotation group, the irreducible representations are these functions, e to the I k theta, where k is a real integer. Now, real integers vary over, like there's infinitely many of them. So there's infinitely many group elements. But this we knew because we already said, even yesterday when we were talking about rotations, you can, you rotate by any infinitesimal amount. So there's an infinite elements, but these are all one-dimensional. Moreover, these are functions that are orthogonal and they're normalizable. Now, if you consider what these irreps do on the vector space, now remember they were acting on the elements of the vector space. Now the vector space has itself a well-defined inner product. And this is the definition of this inner product is such that if you insert an operator on one entry, if you bring it to the other side, if you take the adjoint of it. Now, let's see, what do our reps do to this inner product? So originally we have the inner product V1, V2, but you know, our rep takes V1 to pi theta V1. So this is e to the ik theta V1, and it takes V2 to pi theta 2. So this is e to the ik theta V2. So now if you look at it like this, so if you consider ik theta V1, ik theta V2, now this is like the having inserted an operator A here, but I can just bring it to the other part, and it will be like this, and this just gives 1, the unit element. It doesn't change the inner product, so it doesn't change the inner product defined on the vector space. Such representations are called unitary, the representations that preserve the inner product. Okay. Now notice two things. We found the irreducible representations of SO2 to be one-dimensional. One thing to notice is that we found finite dimensional representations of a compact group. This is a general thing. Remember yesterday we said compact, okay, there's a concept of group, but then within this, there's a category of compact groups and a category of non-compact groups, and they have some differences. So this is one of the differences. Unitary irreducible representations of a compact group are finite dimensional. I did not write it. R's of a compact group are finite dimensional. Now, on the opposite category, for non-compact groups, the unitary irreducible representations are infinite dimensional. So this is why when you talk about spin, you talk about finite dimensional representations. For example, you have the spin S, and then there's this eigenvalue along the Z direction MS, and you have the eigenvalue along the Z direction, and then there's some J values that run from minus M to M. So that you only have those many things. So that's a finite dimensional representation. Now, we could just construct these SO2 representations because SO2 was a other simple group. It didn't have any further subgroups. But what happens if we have a bigger group that's composed of more subgroups? Then there is a technique. You look at a certain subgroup of that more structured group that's called the stability group. So this stability group leaves some things invariant. For example, for the Poincare group, the stability group is called the little group, and it's the set of transformations that preserve a reference momentum. And you build your representations considering what happens to what keeps a reference momentum preserved. And then there's a few versions that you can pick these reference momentum. So I don't know, maybe you just fix the 0th component of it, set the other components to 0. That's one reference, or something else, that's another reference. And you build the representations for each possible categoric references. Now for the Suture group, we found all these subgroups. These are, each one of this is a transformation we found. We found dilatations, spatial rotations, spatial conformal transformations, spatial translations. There's also, so each of these form a subgroup, but there's a bit more than that. There's also something called a maximally compact subgroup. So this is like spatial rotations in one higher dimension. But now we will not drive things. It will be more like I give you facts. But the stability group of the Suture group happens to be the composition of dilatations, spatial rotations, and spatial conformal transformations. So the representations are built from these. So these group elements are important, have an important. The elements of these following subgroups have an important role in building the representations. And we will always denote the group element by a lowercase version of how we denote the group. Now, so then sort of one thing to think on is the representations of, what works into this. Now, one thing in this stability group is the rotations. We know that these irreps are labeled by spin. So, and we will just denote them with these DLM matrices. So for each rotation element M of a given spin L, you have some representation. Now, dilatations and special conformal transformations were transformations to do with scaling of directions. And well, in the case of dilatations, this was just scaling by something constant. Now, irreducible representations of dilatations are labeled by what is called the scaling dimension. This is as such. So if you send the coordinates x to lambda x, an operator changes like this. So in terms of the new coordinates and in terms of the old coordinates, an operator that transforms like this under the dilatation, where the amount of scaling you did comes out by an exponent. This exponent here is the scaling dimension of the operator. And so these irreps are denoted as the group element up to the factor of minus the scaling dimension. So these are also important things. So spin and scaling dimension are important things when you label the irreducible representations of the Suture group too. But something interesting, some interesting property exists for this, for the SO1, D+1 group. This scaling dimension, I mean, this is not the only group that has scaling these dilatations. But in this case, this scaling dimension has a fixed format. So the number D, so in a physical sense, this is the number of spatial dimensions we have, works into the scaling dimension. And then there's a more free piece, This can be real or complex or purely imaginary. So in general, it can be complex. And this is called the scaling weight. So because a part of the scaling dimension is fixed for any representation, this whole scaling dimension itself, I mean, rather than the scaling dimension on the whole, this free piece means is more categoric. So the representations, for the representations, these labels L and C are important. Now, what is the academic educated way of labeling these irreducible representations? It's to look at the eigenvalues of the Cosmere operator. Now we are talking, remember, so far we've been talking about the group elements, but remember that this was a Lie group, and for a Lie group, you also had a Lie algebra. So you had, for the group elements, you had some operation, and then, but in the case of a Lie group, you could write these group elements in terms of generators. And for these generators too, you had some operation that was the Lie algebra. So there will be if you like, these are the basic elements. These generators are the basic elements of the Lie algebra, but you can compose more complicated structures from them. Like you can add them together, you can multiply them with each other, you can make more composite operators out of them. So the Cosmere operator is one such operator. That commutes with all the elements of the algebra. So these elements are generators. So let me write it as generators. Okay. Now it's not just one. You can build it at a quadratic level, at a quadric level. So to the power 2 to the power 4, it can go like this. But for SO1, D plus 1, this is what it is, what the quadratic Cosmere is. So notice that the notations come with squared, but they also enter in linearly. These are the, these denote the translations. Let's see. Yes, special translations. These are special conformal transformations. This is just spatial rotations. So it's like this, and you know the algebra, like the commutator of CI with TI, all these things. So you can just look at it, and using that algebra, you can, for yourself, like you can check that all these will be 0. Okay. So, so this is an important element. So this Cosmere operator carries important information, and the eigenvalues of this Cosmere operator turn out to have spin and the scaling weight. And so the first thing to note about the Suture group is that its irreducible representations are labeled by spin and scaling weight. Now, if you want to compare, let's say for Poincare, the Cosmere operator is something different, the subgroups are something different. These labels turn out to be spin and mass. So there is this difference. So at the level of representations, the first difference we notice is just this: you label irreducible representations differently on the Suture than you do on Minkowski. Now, the unitary irreducible representations of this group, SO1, D plus 1, have been long known in mathematics literature. In fact, there is a single person who developed, or who was the starting point on the development of all this literature. It's called Harishchandra. And then, of course, other people worked on it. And today, there is even pedagogical books on it. So this is so there is one book by Dobrev and collaborators. How to say a full length. review on the subject. But okay, so maybe this is not so easy to read all at once. But then among the people who worked a lot to develop this, there is the names Gelfand and collaborators. So these worked a lot on 2 dimensions. So they worked on groups like SL2R, SL2C. These are some 2-dimensional. So some of the representations of SL2R correspond to representations of the Suture group in 2 dimensions. So they worked in groups that have that also have some part of the Suture in them. And then there is one reference that I would like to point out is by Barut and Fronstad. So this Barut is Asım Barut. And okay, now I don't remember the name of the paper, but it will be in the references list. And what they do is they study SO2,1 reps and compare it with SO3 reps. And they do this by looking at the algebra. So I think, like, if you wanted to read something more at the end of this lecture series, I would point to this as the first thing. Okay, so it's an old paper, but I think it makes some nice points that if you spend time on it, you can understand a lot of the calculations on it. But even if that looks like too much, even at a first reading, there is some nice points they make. And because probably you are more familiar with SO3, it's nice to see it in comparison with something you know. So a lot of people worked on this. And later on, I will also let you know about more recent work along these lines and more references more closer to today. But at the end of the day, what did they come up with? They found out that the representations, the unitary irreducible representations of this group are categorized with respect to scaling weight. And they fall under 4 different categories. And then within each category, you also have the spin. So first category is called principal series. And for these, the scaling weight has a purely imaginary value. Now, this is a bit surprising, right? Like, you don't have imaginary mass, but you can have imaginary scaling weight. So this is, okay, something strange, maybe it's something that hits you in the eye, but it's a property, again, that sets this Suture group apart from the Minkowski group. Now here, this is a imaginary scaling weight. In all the other categories, you have real scaling weight. But now it's not just over anything real, that they divide further into different categories depending on the range. So there's a complementary series. So these will divide into L equals 0. In this case, this scaling weight varies between minus d/2 and d/2. And then there is spin and the range differs. So, I mean, different spin. There is exceptional series. So this is for scalars, this is when the scaling weight is at the, where we stopped the complementary series. And then there's one more called discrete series. And for these, the defining property is that the scaling dimension is an integer. Okay. Now, these we said are unitary irreducible representations, and we said unitary irreducible representations preserve inner products, preserve well-defined inner products on the space on which they are acting. So depending on the category, and we will see this in more detail, slowly, but having the scaling weight to be imaginary or real leads you to do something different about the well-defined inner product. So if you have two of these representations, if this is the inner product for the principal series, so you just don't do anything. You just have to think of like the adjoint of the representation. This is fine. But in these other cases, you need to, how you define, okay, let me say it like this. How you define the adjoint changes. You need to include in an operator, and what this operator is, an operator. And what this operator is different for each of these cases. So it has a different G, okay, call it G tilde. This is also different. So this is one thing that comes out of this, the scaling weight being real or imaginary. Now, actually, in the rest, we will, in the rest of the discussion, there is something in the chat. Okay, thank you for the reference. In this, okay, by the way, the reference is a book, but the reference I'm giving is different. That is a paper, so just, but good to have a lot of references. So in the rest of the discussion, is aims to help you see more of what this operator G is, at least, and let us stick to the case of just scalars, okay? But now, to understand this inner product, now building the representations, you can go two ways. You can look at the algebra, you have your generators, and then you ask what are the states that this algebra acts on, how they transform. Or you can talk about function spaces on group elements. Now, if you go this generator way, the algebra way, you see that for each category, so you want to define normalized states. Okay, so say you started, like you started with some state like this, but you say that this is normalized, some normalization. Okay, so you find that the normalization for principal series states is some number that is different than the normalization for, say, complementary series states. So this is what the Barut and Fronsdal paper explicitly work out. Now, more recent work along this line are the works by these authors. The first one actually considers charged scalar fields on ADS2, but the isometric group of two-dimensional ADS is 2,1. Remember ADS D plus 1, we just mentioned this, was 2, D, but when D is 1, it's just 2,1. So this is just in the two dimensions, something special happens. And this is the same as the isometric group of DS2, which is 2,1. So they study things on ADS, but because they're doing this in two dimensions, they come across things specific to the Suture. This Anus and Skolte is this is also a 2-dimension, let's see, ES, conformal field, a conformal field theory construction. And both of these references, they focus on principal series representations. So you can read these, at least some sections after this lecture would be like nice for you to read. And then there's also a recent review that handles both, actually, I think it handles both this generator way and also the function space way. But anyway, so this has scalars and integer spin. But now we will go this way. We will go with the function space way. And we will follow this, this review by Dobrev and collaborators. And actually a lot of what I found, what I say can be found in work with Konstantinos Skordis. This is like 2 works back to back in 2 different years. But this one in particular, one of the sections of it is like a review of this Dobrev reference. But so now, what is this building function spaces? These are functions whose entries come from the group elements and who have values in a vector space, which is the Hilbert space on which the unitary irreducible representations of the rotation group are realized. So not just any random vector space. And moreover, there is a condition. If you take this combination, so this is a random group element, but if you take the composition of it with an element from special conformal transformations, dilatations, and rotations, it has to satisfy this. It comes back to the function of the element of interest scaled like this with these extra in the front. This is called a covariance condition. And the homomorphism in this case is you act on the functions from the left with the inverse. And you can show that this also preserves structure. So remember in the rotations, we were adding things. So in this case, this is the homomorphism that works. And now, and on this function space, the well-defined inner product is as follows. You can re-express these functions. Remember, our functions were over group elements, but they have a connection to functions over the real line. And this is, you know, like in physics, we work with fields. Fields are over the real values. They're oval coordinates, for example. So this is, so there's a connection like this. And so the inner product is based on the rotation invariant inner product on the position space. Now we will do something. So I said there's a connection. Wait, let me find a different color. Connection between group elements and position space. this is as follows. Now for each element of the position space, there is a uniquely corresponding translation element from the group, such that the value of the function at that translation element matches the value of the function at the position element. And also there is a uniquely correspondence between an element of the group, of the whole group, such that this is satisfied. So this xg denotes the x corresponding to the g of interest. Let's see, until the x denotes until the corresponding to x, xg denotes x corresponding to g. So that's to a specified g. Moreover, the volume elements are related as follows. So just the presence of dilatations does something extra to the volume. Now, let's ask, what does our rep do on functions of this function space? No. Okay, what does it do? So let's look at this. We know we can write this over the position elements. Like this. Now, what do we know about the representation acting on the functions? We know how it acts on a general group element. It acts like this, but we kind of want to understand how it will act on RD, so on X, on the axis, on the coordinates. For this, we can look specifically at an element of translations, because we know that's where these functions over group elements match with functions over real line. So just look at this. Look at this specific case. And X, this will be, okay, just some F. This will be G inverse until the X, but we also know what this is. Remember this? Star. Now, it was a condition of our function space that if you come across the function with this, with such a combination in its argument, you know that it factors out like this. In our case, it's just with the inverses entering in. So it's just the inverses of A and DLM. So we have this here was DLM inverse, but we are doing the inverse version, so that's just DLM F n tilde xg. And we know that this is fx. So all this we can recognize as the way our representation acts on functions over real space. So now we can make use of this expression here. So if you go back to what our representation does on the inner product of functions, we get this. Okay, maybe I will put a bar instead of 2 commas so that it's more apparent. F2 X. Now, we talked about, so we said that an operator on the first entry moves to be an operator on the second entry by its adjoint. Okay, so using this, we can just keep moving these operators on the bra towards the cat. So these, okay, let's leave that there for now. Now, being the representations, being unitary distributed representations of SOD, this DLM dagger, DLM is just identity. So this drops out. Oh, sorry. Okay. And these factors of D2 minus C are scalars. I mean, they're just, so they just come out, but you have to be careful. C in general is complex. So when this factor comes out, so this is equal to, it comes out with its complex conjugation. X, okay, it comes out like that. So altogether we have ddx minus d minus c plus c star. Sorry, this for xg's here. Remember our, oh, this is important. Yes, this is xg. Okay. These are xg's. To xg. And also remember here that ddl a minus d was d dxg. So altogether we found g f1 by g f2 to be so just something to do with dilatations up to the exponent of scale link weights remain as some extra piece. Now, if you compare the normal inner product the well-defined inner product on the function space was as follows. At this point, at this point, these are just integration variables. So these are the same. Now, if to be unitary, if this representation is to be unitary, we said that it shouldn't change the inner product on the function space. It should satisfy this. But here, when we explicitly calculate the left-hand side, we note that there's something extra. There's an extra piece compared to the right-hand side. Now, for C, purely imaginary, this piece automatically drops out. Okay, so this is why this is one category. So we said this was the principal series category, and this is why the principal series inner product is straightforward. Okay, remember in the up there. In our list. This is why this is straightforward. And we said in the case where C is real, it's because that A to the power C plus C star remains. You need to do something. You need to insert an operator to take care of that. So this takes care of the A to the C plus C prime factor below. Okay, so what is this operator? So let's say C is new, which is just real. You need a G such that it takes an operator with scaling dimension plus C and sends it to an operator with scaling dimension D over 2 minus D. So, but it doesn't change the, spin. So you need something, let me write it like this, that takes LC and sends it to L minus C, okay? Such an operator exists, and it turns out to be invertible. And it carries out a similarity transformation. So it actually doesn't change the representation. It gives you a similar version of it. And it does this for you. So these are called intertwining operators. Also the transformation they do can be called a shadow transformation, but just, okay, now I will not, it's like this, it's shadow transformation satisfies some relation like this, but now I'm not sure if this is a plus or a minus. So let's not write that, but this transformation satisfies that some specified combination on the scaling dimensions. That's how it can be recognized as such. And the way this is defined, so has expressions in position space, but also in momentum space. So you have like G chi, K, G, K. In position space, it looks something like X minus Y, X minus Y. Okay, maybe there's a plus or a minus. Right, but it looks something like this. And this is the expression that resembles the 2-point functions here on the Suture. And in momentum space, it looks like K to C, but actually we will write this more carefully. So I will write this out explicitly for you. But now this is, we said this is an invertible operator. It's also normalizable. Now these two steps you need to be careful with, that it gives you back a similarity transformation and that it is a normalizable. The details of these properties change between discrete, exceptional, and complementary series. That's why you have these three categories. They have different G's defined for them, okay? Hence the difference. Okay, we have like half an hour, right? Okay, so we have time for the example. Okay, now let's look at this. For scalars in the complementary series. This, so we have 0C. Now, so there is G chi and then there is its inverse. So this is actually inverse. And one of them is well-defined for C greater than 0. The other is well-defined for C less than 0. So this is well-defined as a operator from the function space that hosts the transformed operators. So this is the function space with 0 minus C, and this is the function space with 0 plus C. And this is well defined for C greater than 0. And with its, this is specific normalization. There's a few versions. In momentum space, it has the following for scalars. So this just means C minus C. And then its inverse is defined as a map from the function space to the transformed functions space. And this is well defined for C less than 0. And this is defined as now, how do these work? Now, let's give an explicit example from the late time boundary of the Suture in any dimensions in planar patch coordinates. So this is okay. This example is thanks to a Marie Curie fellowship. Now, study a non-interacting scalar field of arbitrary mass on the Suture, and it doesn't affect the geometry, okay? Such that it doesn't affect the geometry. Okay. And it satisfies Bunch-Davies initial conditions. This means at early times, it behaves as if it was on Minkowski space. All of this, so you write down your action, but it only has a mass term. It only has m squared, phi squared in it, and the derivatives, of course. And you find the equations of motion. You look for solutions with these initial conditions. Solutions come in the form of Handcap functions. And this field is quantized. So you can decompose it in terms of annihilation and creation operators. So that is operators that there's annihilation operators. When they act on what is the vacuum, they just annihilate it. And then there's the creation operators that when they act on what is the vacuum, they give you states of momenta k, okay? So the solution for this field comes in terms of Handcap functions, but there's two types of Handcap functions. There is those with a real index, and then those with an purely imaginary index. But you can also write as some, there's some factor like something like this page, or maybe the other way. These like imaginary index Handcap functions are also denoted by this H tilde. And this, so you hit upon either Handcap functions with real indices or with imaginary indices, depending on how heavy the mass is with respect to the number of spatial dimensions and Hubble parameter. So solutions split into two branches. So one branch is this. So this is the number of spatial dimensions. This is the Hubble parameter, which is just a constant for the Suture over 2. So this is one branch, and the other branch is the opposite, okay? So it looks like this. Let me just write this out. In planar conformal time coordinates. So it's everything with a real index Handcap. Okay. Row and new are real and positive. Now, you know the properties of Handcap functions. You know how to take limits as the argument goes to 0, as the argument goes to infinity. So if you look at it as eta goes to 0, this is the late time. You just study what the Handcap functions do in this limit. And it turns out that these fields come to be as follows. So the spatial dependence, there's one more term, and the time dependence factorizes. Okay, and here you have imaginary exponents in the heavy field case. And what these alpha and beta are just operators. You just read it off from the solution. First, you see that it has a shape like this. And then you look at, what all this taking the limit argument goes to 0 brought from this Handcap function and its complex conjugate. And these come out to be built out of annihilation and creation operators. And they have some overall momentum dependence that matches this exponent. So the amount of annihilation and creation operators are not so important. Let's just some m n. Okay. So these are like some gamma functions to do with I rho, some cosine hyperbolic functions to do with I rho, so things like this. Okay, there's some factors, some numbers for alpha h. Okay, and then for beta hk, you get again some different numbers. Plus ik, okay? What is important is on one side you have this k to the minus I rho, and the other you have this k to the plus I rho. Now something similar also happens for the light field case, and there you have a light operator. So okay, there it's, instead of these I rhos, you get news. So this has like, this has a d over 2 minus the piece and a d over 2 plus new beta light piece, okay? So, and here it looks like, again, some letters. Okay, actually, just let me write. In one case, it looks like this. Some, again, just general coefficients. Now, these operators are defined on momentum space, but you can always do a Fourier transform into position space. So like this OX will be okay. And either you look at it like that, and then you study the dilatations, or you just look at it with the dilatation generator. But you find out that Lx scale by delta d over 2 minus mu, L heavy x scale by d over 2 minus I rho, and beta light x scale by d over 2 plus mu, and beta heavy x scale by d over 2 plus I rho. Now, this is the way the dimension of the Suture, this is the way the Suture representation scaling dimensions worked. And we can read off that we have these scaling weights. Okay, so the light ones correspond to C plus, minus plus nu. So you expect these to be in the complementary series, whereas the heavy ones correspond to C minus plus I rho. So you expect these to be in the principal series. But let's put question marks, okay? Now, dimension-wise, they fell into these two categories just because of the way the functions came out to be. But these two branches are also following the branches of the representation theory categories, okay? But to make sure of this, we should also see if they follow the, the well-defined unitary inner product. Now, what we can do is from our, let's take a light one. Okay, and let's just write it like this. For some mass, you can find this. Okay, I want to say don't worry about the coefficients, but then I think maybe let's keep it. Actually, let's take a beta. Beta key to do plus mu. Now, from this we can define a state by acting with it on the vacuum that gets annihilated by the annihilation operator. So we do this, we define a state. Okay. So this was meant, and it's just going to pick a contribution from this piece. So it will be mk plus nu minus k. Now the ket for this, sorry, if this is the ket, the bra for this would be the adjoint of this. But k to the power nu, because nu is real, nu was real. So it just gives you this. Now, if you wanted to compute this BLK, BL, just like this, and you took this definition, if something is like, if something gives you up to Dirac delta, it's fine. But if it gives you other divergences, it's not a good sign. this was the definition of the inner product. But this piece.
Gizem, sorry for the interruption. You have 5 minutes left. Just a reminder.
Okay, thank you.
And by the way, you can take a bit more time because Deniz will use less time than usual. So maybe you can take 5 more minutes.
Okay, okay.
Just to complete the discussion.
Okay, thank you. I will try not to take too much time. But now you saw that this has something like K to 2 nu, the Dirac delta. If it is just this is fine. I mean, you just call it Dirac delta normalizable. Fine, we can live with this. But this becomes problematic. That operator you can check for yourself. So you can you can find this B tilde operator. So it will be G chi acting on B. And this G chi was, so this is C greater than 0. I have it written on paper. Greater than 0. So for that, the well-defined operator is the G chi tilde 1. So this is just squared minus nu. And so this one will be times beta operator. Okay. So overall, this will have whatever those annihilation creation things were. But there's a K minus 2 nu, K nu. So overall, you have K up to minus nu. So now if you define a state from this, so if you look at this state, this has no K, it has like K to 0. So it doesn't, this is fine. This is fine. You see? So this is what so thanks to the complementary series, inner product, we can have Dirac delta normalizable states from beta. Now, in the principal series case, instead of this nu, you have I rho. So even at this level, so principal series case, this will be M I rho, and the opposite one will be K to the M minus I rho. So these will just cancel each other. That's why you don't need to do anything extra. So this is the kind of thing that intertwining operator that we had to put in the middle for the complementary series does in some physical sense. But you can do these kind of exercises, and at the end of the day, what do you get? We knew from the beginning that the de Suture geometry had 2 boundaries along the time direction. Okay, and now we investigated, well, very briefly, some operators at this chi plus at the late time boundary, and we could check that these indeed act as unitary irreducible representations. So there is a way to equip, to take a question of a scalar field on the Suture, which you calculate its its correlation functions. So all these things. You can calculate more with interactions, but these are calculations done in cosmology. But now there's a way to rewrite it in terms of some operators at the boundary that you can represent as unitary irreducible representations. And of SO1, D plus 1. Now, so at this stage, what did we do? We talked about the representations, but we saw there's a little bit of a difference between these representations and Minkowski representations. And okay, we saw that fields on the Suture we can recast, like we can bring the representation nature of it immediately. There is also references for a construction for finite eta. So this means inside the, not at the boundaries, but inside, so in the bulk. Okay, let's call this bit the bulk and boundary. But if you start building these things, you can also ask, is there a holographic side to the Suture? What I mean by this, now in the beginning I said this section was going to be holography motivated, but take holography as a tool that tells you that gravitational theories on some curved space-time, but this is not very general, can be recast as conformal theories that just live on the boundary. Remember, you saw in the first day's seminar, in Mert Beşken's seminar, you saw an example of a conformal field theory. And what they were doing, they were talking about correlators, OPE expansion, all these kind of things. Now, the way to explore this idea is to calculate, and these objects had some dimensions, right? Is to calculate, is to try to see what the dimensions, the scaling dimensions would be, what the allowed scaling dimensions would be on this side. And again, calculate some correlation functions on this side. Now, these operators that you find are not immediately the CFT operators, but all this gives you hints on what there is on the CFD side. Okay, and this proposal has been put forth with explicit examples on the Suture space, whose isometry group was so if this is D+1, D(2). Now this isometry group also happens to be the conformal group of Minkowski in one less dimensions, 1, D-1, let's say. Now we looked at the Suture, and for the isometry group, we found this to be SO1, D+1, but this is also the conformal group of Euclidean space in one less dimensions. So now this is just first clue to ask that maybe this concept that was developed on the Suture spaces can be something that applies even further. Of course, the exact details of holography are much more than just working with the isometry group. You have to also consider like the gravitational pieces, the geometry changing. You have to consider all of this. This is why this would just provide as a first clue. But even based on this clue, some examples started to be built up. And then there's something more. There's also Minkowski. And people also asked, is this holographic as well? And they started developing this framework of celestial holography. So in this story, whether you think about quantum field theory or holography, there is room to ask, is it something developed just for the specific space-time we see when we open up the textbook? Like when you open up the QFD textbook, it's actually a book on Minkowski, but how will it be on some other space-time? And when you open up like, well, you will mostly encounter these ADS-TFT examples. So that's holography on ADS, but how is it in other things that seem to possess conformal symmetries? There is one more thing. Now, these are not just any random spacetimes. So we said ADS, we said de Suture and Minkowski. And to go back to the very beginning, these are all spacetimes with maximal symmetry. And they're all solutions to the Einstein equations with a cosmological constant at a different value of the cosmological constant. So the cosmological constant being positive, 0, or negative. So maybe because of this, they all seem to lead to this. I mean, like, you know, this is something to think on, like for all of us, for the whole community, that we have this tool, holography. It seems to be very nice for understanding gravity on anti-de Suture spacetimes. But if we put anti-de Suture as a member of this bigger family of maximally symmetric spacetimes at different values of the cosmological constant, then how far does the reach of holography stretch to? And for each case, for each lambda, it will be different. You have to treat the analysis individually. But so I told you very basic things like Penrose diagrams and representations, but all of that can be repeated for a lot bigger, more general questions. And this will be my last sentence.
Thank you so much, Gizem, for this beautiful lecture series. We were quite, we are so happy with what you have been talking about. And before we stop the recording, are there any questions from the audience? Okay, and one small note, like all of these are kind of related to each other. If you haven't been to the summer school we have organized in September, you can actually talk about the string theory, and here the lecture says he also introduced some ADS concepts which are closely related to the digital computations. I also talked about the conformal symmetry and conformal bootstrap, which are also kind of related to these representations and their utility in system mechanics, etc. So I recommend, if you are interested in these concepts, to check them out. Okay, so I'm going to stop the recording.